Hello, everybody. It's Ryan Powers here, your favorite programmer, and we're going to do today LeetCode number 4, median of two sort arrays. Pardon my speech at the moment. I went to the dentist today, got some work done, but we're going to power through, and we're going to put this video out anyway. So the problem we're doing today is median of two sort arrays. This is actually a pretty cool problem. It's a pretty challenging problem. So I definitely encourage you to try to solve it first before going all the way through this video. But let's just introduce the problem here real quick. So there are two sorted arrays, nums1 and nums2, of size m and size n respectively. So they could be of any size. They don't have to be the same size. So one could be smaller, one could be larger, one could be empty, one could be full. So you just have two sorted arrays, and we need to find the median value. So one assumption that we get to make here between nums1 and nums2 is that not both arrays are going to be empty, right? So at least one of them is going to have some number of values in them. And here's some examples for us to look at. So we have 1, 3, and 2. The median value of this array here is 2, because if you put these arrays together, 2 would be the middle value. So that's why we get 2 here. So here's another example, 1, 2, 3, and 4. So because the length of this array is an even value, we actually take the two middle values, which in this case are 2 and 3, and then we take the average of them. So that will give us the midpoint between those two middle numbers, which will give us the median. I will drop a few hints about how to solve this problem. So if you don't want to keep going with the video, I would solve the problem and then come back and check this out. But so there's 2 bits of information here that are, well, there's 3 bits of information here that are really important. So the first one is that the solution, the runtime complexity of the solution should be of log m plus n. We're actually going to do it in log min of m and n. But this is a big clue here to tell you that you should be having your search space each time you iterate through with your algorithm. So that's kind of a big clue there. And then also both arrays are sorted. So that means that they're pretty easily searchable using binary search. So that's the strategy that we're going to use to solve this problem. So we're going to use binary search and the fact that these arrays are sorted to find the median value. So come with me to the whiteboard and we'll check out the strategy we're going to use for solving this problem. Welcome to my whiteboard. I've gone ahead and drawn out an example for us to go through. And what I've done here at the top is I've just merged these two arrays into sorted order into one array. So we can kind of see, all right, what is this array supposed to look like? And what are we supposed to be returning? So the median value here is 11. So that's the answer that we're after in this problem. And the reason why we're looking for 11 is because we have 5 values on the right, 5 values on the left and 5 values on the right. And that is going to be the median, which is 11. So this is the simplest way to solve this problem, which is an order n solution, where we just take the two arrays, we merge them into one array, and then we just divide the length of the array by 2 and return that value at the midpoint of the array. But what we're trying to do is we're trying to solve this problem in log min of n and m. So the first thing we need to do is define, okay, which of these arrays are we doing binary search on? So since we're trying to solve this problem in the log min of n and m, we're going to do binary search on the smaller array. So the first thing we need to do is we need to split our search space in half, right? So since this is a small array, we'll just draw a line straight down the middle, or we'll define the middle as being 3 values to the left and 2 values to the right in this particular circumstance. And so what does that tell us? So since we split this array with 3 values to the left and 2 values to the right, we're saying that these 3 values here are going to be in this left group. And we're saying, okay, these 2 values here are going to be in this right group. And what we're after is, what we're going to be doing is actually on these odd arrays, we're always going to be putting the extra value, or what will eventually be the answer, in the left group. So what we're looking for is a split of 6 to the left and 5 to the right. So if we draw this line here and we put 3 values in the left group and 2 values in the right group, then that means that we have to put this line, and this large array can go in no other place but right here, right? To achieve this 6 left group, 5 right group, then that means that we have to draw this line here. So the next thing we need to do is check to see, okay, is this a valid split? And to do this, we can look at the 4 values that are straddling this line. Okay, so that would be 8, 18, 9, and 19. Okay, so we're going to define 2 variables here. The left variable is going to be the maximum of the 2 left numbers, which are 8 and 18. And that's going to be equal to 18. And right is going to be equal to the minimum of the 2 right numbers. So that would be 9 and 19. So that would be 9. Okay, so the test that we can use to see, is this a valid split, is left less than or equal to right? If it is, then it's true. Then we have found the place where the median exists. Where if we draw these 2 lines in these places, that means we have found the place where the median exists. If it's not true, then that means we have to keep looking, and it's false. So why is the left the max of the 2 numbers and the right the min of the 2 numbers? Well, if this was a valid split, then that would mean if we're looking at this large array here, we would have we're eventually looking for these 4 numbers right here, right? So for this statement to be true, then the 2 values to the left of the line, the maximum should be less than or equal to the minimum of these 2 numbers on the right side over here, right? So these would be our 2 right side values, and these would be our 2 left side values, and that's what we're looking for. So we know that we've found the correct split if this statement is true, if left is less than or equal to right, because there could be the case where we have duplicate numbers, right, where maybe both of these numbers were 11, and then that would still be the median. So left can be less than or equal to right. So since this is not true, we now need to know, okay, which way do we need to go? Like, where do we need to search now? So if we look at the values here, we can look at the left number of the small array, and we can compare it to the right number in the large array. So we can say, okay, is 8 less than 19? If 8 is less than 19, then that means that 19 is where it should be. It's on the right side of the line. So that means we need to move our line, or our where we're splitting these values in the small array. We need to move it to the right? Because that means that this 18 here is part of the right group. So we need to move this line over here to the right side, and we need to move the top line to the right. So if 8 was greater than 19, or if 8 was greater than this number right here, say this was 8 and this number here was 7, then that would mean that this line needed to move in the other direction, right? So that's how we're going to decide which space we need to search next. So because 8 is less than 19, and that means that we actually need to move, our line needs to move farther to the right here, then we need to now search this space right here. So we need to find the midpoint of the right side and make a line such that we are finding a midpoint again. So we'll do just that. We'll split our line right here, and that puts 4 numbers to the left and 1 number to the right. And so we're going for this 6-5 split here. So that means we have to draw our line here. right? We don't have any other choice. It has to equal 6 numbers, so we know that we need 2 values. We need 2 values from this large array to be to the left. So now our 4 numbers are 9, 11, 15, and 18. And we'll just do our check again, right? We'll say left is the max of 9 and 11, which is 11, and right is the min of 15 and 18, which is 15. And we can see here that left is less than right. So this is true. We have found a valid spot to split our array. So we know that we've drawn our lines in such a way where the median exists. So how do we know which number to return? Well, if we look at this mess that I made up here in this larger array, we have found this spot here, right? Like this is what we're looking at. So we have 9 and 11 to the left, which we have over here, right? And we have 15 and 18 to the right, which is what we found right here. So we already have a way of deciding what value we want. So if the array is odd, so if array dot length mod 2, whoa, sorry about that, mod 2, if that equals 0 and it's even, then that means we want to return left plus right divided by 2, right? So that would mean the midpoint existed between these two numbers if the length of our array is even. So we would add these two numbers together and then divide them by 2 to get the median value. If it's not even, then all we have to do is return left, right? Because we have 6 values here on the left and we have 5 values over here on the right. So we just return this here, which is the midpoint. Okay, so there is one other small kind of wrinkle to this problem that we're going to go over with a much simpler example to illustrate how we're going to handle that case. So I'm going to do a little bit of setup, and then we'll run through one more small example. Okay, so here's the second example that I wanted to go over to illustrate kind of the last little wrinkle in this problem. So this is a much simpler example. We're just doing 1, 2, 3, and 4. So it's going to take us 2 rounds again to solve this problem. But let's kind of go through our process. And when we hit the little wrinkle that I'm talking about, we can make the small adjustment to our strategy in solving this problem. So the first thing, so our 2 arrays here are 1 and 2 and 3 and 4. So the first thing we do, just like we did before, is draw a line straight down the middle. So we've drawn our line down the middle, and since we're putting 1 value to the left and 1 value to the right, then that means that we have to draw the line in our other array down the middle as well. So that would give us these 4 values for comparison, right? And as we did before, left is equal to the max of 1 and 3, which is 3, and then right is equal to the min of 2 and 4, which is 2. So we ask ourselves again, is left less than or equal to right? It is not. So this is false, right? So we then do our comparison again, where we compare this number to the right value of the other array. So as we saw before, this value is less than the right value in the other array. So that means that this number here is in the correct position. It should be to the right of this line. So that means we need to move this line this way, and we need to move this line that way. So we now need to create a search space on this side. So the only other place we can draw this line is here, right? So that would mean that the line that we drew on the bottom array, would be here, right? So that means that our four numbers are 2, this kind of non-existent value, and then to the right we have 3 and this other kind of non-existent value, right? So how do we handle this case where the array, the way that the median works with these two arrays is that all of the left values or all of the numbers from one array, or the median is basically between these two arrays, right? So we only have two numbers to work on. So instead of what we have been doing, where we just define the max for left as two numbers, we have to create another case, right? We have to say, well, what if the number doesn't exist at all, right? So left, in this case, would be the maximum of 2, and so we'll say if there's no number there, if there's not a number, then we'll say left is the max of 2 and negative infinity. So that way, if there's not another number, to compare, and I'm sorry, I'm talking about these two numbers here, right? 2, and then this would be negative infinity. So if there's not another number to compare with 2, then we want to make sure that we're always taking the number that exists. So by saying negative infinity and taking the max, then any number that we have is going to be more than negative infinity, right? So that's going to be 2. And then right, similarly, only has one value. So we're going to take the minimum of 3 and infinity. So that way we're always taking the value that exists, right? So this could work in a case where the arrays in this instance happen to be of equal size, but you can imagine that there is a scenario in which we're putting all the numbers from the small array on the left, and then we're drawing our line somewhere in the large array, and that's where we're going to find our median value, right? So anytime we're in a scenario where we're putting all the numbers like this, like we're doing right here, where we're putting all the numbers on one side of the line, then we need to then use this infinity and negative infinity to do our comparisons for creating our left and right variables, right? So right is equal to the min of 3 and infinity, which is 3. So we can say, okay, is 2 less than or equal to 3? It is. So this is true, and we have found the correct position in our array. And like we did before, we say, okay, is array dot length mod 2 equal to 0? Okay, in this case it is. This array is even length. So what we need to do is we need to take right plus left and divide it by 2. If this wasn't the case, then we would just take left, right? So in this scenario, we're taking 2 and 3, adding them together, which is 5, and then dividing it by 2, which is 2.5. So you can see I've drawn up here that 2.5 is our actual median for this array. So between these two examples, this is the strategy we're going to use to kind of implement this into code. So why don't we go to the terminal or to the REPL and code out this problem. To code this problem, we're going to use 3 functions, 2 of which are on the screen here, find median sorted arrays, and the other one, check for median. So find median sorted arrays is going to be responsible for doing all the binary search logic and implementing the binary search. And then check for median is going to be responsible for taking the 4 values, the left side values and the right side values, and then determining whether or not the line we've drawn is a valid median. So the first thing we want to do is create a size variable. So the size is going to just be the sum of the two lengths of array 1 and array 2. This is going to allow us to, or this gives us the whole length of the array, and we know that half of that amount is what we need to put on either side, the left and the right. So then we want to define our helper function. So the helper function is going to take a small array, a large array, and then we're going to define the low, and we're going to set default to -1, and then the high to be the default of the length of the array. So when you do binary search, the first thing you need to do is find the midpoint. So we're going to grab the midpoint. So that's going to be the low plus the high divided by 2. And then what we want to do after we grab the midpoint is check this line. Is this a valid line? So we can store a result variable. In the result variable, we can store the check for median. So check for median is going to take an index, which is the midpoint that we just calculated, as well as the two arrays, and then the total size. So the result variable, if we find the median, is just going to return a number. So we can just check for the type. We can say if the type of result equals number, then we're done. Just return the result. If that's not the case, we need to keep searching. So, well, we need to know, okay, are we too low or are we too high? So result, if it doesn't return a number, it's going to return a string. So if the result is equal to low, then we're too low. So we need to redefine the low as the current midpoint. So we'll make another call to helper with the small and large array, and we'll redefine low to be mid, and we'll keep our high. If that's not the case, then we're too high. So we need to do the same thing with our inputting our small and large arrays, but instead of redefining the low point, we'll redefine the high point. So this is everything we need to do inside of this helper function to do the binary search. The only other thing we need to do is make sure that we're doing binary search on the shorter of the two arrays to ensure that we are actually doing log of min of n and m. So to do that, we'll just check to see which array is longer, and we'll do binary search on that one. So if array 1 is longer than array 2, then we'll call helper with array 2 as the first argument. Otherwise, we'll call helper with array 1 as the first argument. Okay, so that's everything we need inside of find median sorted arrays. So now what we need to do is define this check for median, which is going to be all the logic to decide, okay, is this a valid point? So the first thing we need to do is figure out how many numbers we need on the left of the large array. So we can define a variable called nums needed, and we'll set this equal to the total numbers that we need. So the floor of the size divided by 2 minus the numbers that we have already allocated to the left in the small array. So that would just be index plus 1, right? So the current index we're passing in, if it's the index 1, then that means that the 0th index and the first index have been allocated to the left side. And if we want to say that there are two numbers there, we can just take that first index, just add 1 to it, and say, okay, there are two numbers allocated to the left. So now we need to define our 4 variables. So that would be the small left side, the large left side, and then we want to do so small right that didn't help. Small right, and large right. Okay, so we have small left and large left, small right, and large right. So these are the four numbers we're going to use to define whether or not it's a valid median. So small left is going to be equal to the small array at index. If that value doesn't exist, we'll just set it to negative infinity. Large left is going to be equal to large at nums needed. That was my wife. At -1. So if we say we need 4 values allocated to the left side and we subtract 1 to it, then we want the third index, right? So if that's not, if that number is not defined, then we'll set this to negative infinity as well. So then small right will just be that index at index plus 1, or infinity, and large right will be large at just nums needed. And similarly, if this does not exist, we'll set this to be infinity. So with this in place, we have our four values. And now we just need to define what is left and right. So as we discussed earlier, left is the max of small left and large left. And right is the minimum of small right and large right. So now that we have these two values, we just need to do our check. So we say that if left is less than or equal to right, then we can return something, right? If the total length of the array is an even number, if the number of values is even, so if size mod 2 equals 0, then we need to return right plus left divided by 2. Else, we can just return right. So before, when we talked about this problem, I said we were going to put the odd numbered 1 to the left, but it was easier to code to put it to the right. So in that scenario where we had 6 numbers on one side and 5 numbers on the other, well, that 6th number is going to be on the right side. So if it's odd, we'll just return this right side value. So if this is not the case, if we didn't find the midpoint, then we need to either return if we're too high or too low. So if the small left value is less than the large right value, then we're too low, right? Because this large right value is where it should be. So we need to move the small left value further to the right. And so we can just return that it's low. And then if this is not the case, then it's too high. So with all this logic in place, we can just do a quick little recap here. We grab the total size, we define this helper function, which does our binary search for us. We're finding a midpoint, and then we're passing it into a call to check for median. So check for median is going to take our midpoint, and it's going to figure out how many numbers do we need to the left. Using these 4 values, it will determine a left and a right. And then if it's valid, if left is less than or equal to right, then we can return our value. If it's not, it's going to say whether we're too low or we're too high. And then here at the end, we're just stating that we want to run binary search on the smaller of the 2 arrays. So if we click submit here, okay, I'm getting a runtime error. line 34. Let's see. So if result equals low, so mid, high, low, mid. Unexpected token. Okay. Oh, okay. I need a question mark here. Another typo, line 29. Okay, with the typos out of the way, a little live debugging. We've come to our answer. So as you can see, I've already run this a few times. I've been working on this problem for quite a while, actually, trying to write it in a readable way that's easy for me to explain. But I've actually run into some really interesting results that I wanted to show you. So you can see here that I'm actually getting some pretty variable run times. Like I'll get 152. I even got a 216 down here. And I was pretty surprised by this. So I wanted to investigate some of the solutions and show you guys a little bit about how you can kind of check your own runtimes. And when you get these kind of funny results from LeetCode, I found myself in the past just hitting submit over and over and over again until I get a value that I really like. And I'm starting to learn that maybe that's not the best way to kind of go about checking your solutions. So if you look at some of these solutions, so you can see that ours falls kind of in this 80th percentile range. But here's one that I found that's 112 milliseconds. And this here is actually a linear function. So if you see here that they're calling this merged this merged array, or they're defining it, and then they're defining these 2 pointers, and then they're just pushing these numbers in. So this is part of a merge function, and they're just saying that if the length is even, right, then return the 2 middle numbers divided by 2. If it's odd, then just return the middle number. Right, so this is the simplest solution to this problem. It's a linear solution, but you can see that it's only 4 milliseconds slower than what we've done. So if the work that we've done is supposed to be actually quite a bit better than this, the tests are definitely not reflecting that. Especially if I'm sometimes getting a runtime that's twice as long as this 112 milliseconds. So I just wanted to do a little investigative work and show you guys maybe how you can look at these yourselves, and maybe you should take some of these LeetCode results with a grain of salt. But so here's something that so it's not here, it's here. Okay, so right here is that linear function that I was telling you about. So I pasted it into the console here. And then here's our function. So it's I called it check or find median sorted arrays too. And then I used this decorator function that a friend of mine actually mentioned to me that I should try to kind of show how this is working. And what I've done here is I've created, so I've renamed it to linear, and run it through this time decorator. So this time decorator is going to just basically, right before you run the function, it's going to take the start time. And then when you're finished, it's going to give you the end time. And it's going to just spit out like how fast did this function run in. And I did that for both. So I called this the linear, and then this the binary. And then I made 2 giant arrays, A and B. And then we just ran them. So you can see here the linear one ran in about 1.5 seconds, right? And then the binary function ran in 2 milliseconds. So you can see that the runtime for these is actually quite a bit different. And this one problem ran in 1,453 milliseconds, whereas the runtime of the total test suite for LeetCode for the problems that we did was 108 milliseconds. So I would just take those results with a grain of salt. I would focus more on your implementation of the problem. And if you're getting kind of these strange results, I wouldn't just pound on submit over and over and over again to try to validate the work that you've done. I would recommend that you actually investigate it this way to verify that what you've done is actually a good solution to the problem. Anyways, this has been a very long video. It's been a really complicated problem. It took me a long time to go through this, and I spent quite a bit of time coming up with this solution. I hope you enjoyed the video, and congratulations if you completed the problem and made it all the way to the end.